Okay, good afternoon. Are there any questions from last week? Do you have any questions? How was the homework? I've been teaching this class for 10 years now. This is the 10th time I'm actually offering this class in this department. And the first time around, someone complained to me about the homeworks. And the complaint was regarding the Lisp language, and your colleague was, or your classmate was saying that we haven't learned Lisp, but you are, or I am asking you to actually implement rather complex algorithms, not necessarily very complex, but some algorithms in Lisp. And so this is the first time I'm getting this kind of complaint. And as I said in the beginning of the class, or the first lecture, I mean, this is an advanced course now. This is not a introductory programming course. So you already know a lot about programming by now. And you are able to actually learn a programming language by yourself. And this is one of the aim of this course, that we want you to actually be able to learn a programming language and do something useful with it. In this case, homeworks. I don't know how useful the homeworks for you are, but it is for me useful. And I'm expecting you to be able to actually show that progress from your end, that you are able to actually learn and apply. So there is no other way around it. I'm not gonna, I mean, it's not gonna make sense to, let's say, write a compiler in this course in C, and that's another course. That's usually a elective course, a technical elective. Sometimes you offer that on the 5th, 7th, or 8th semester. Okay, so I just want to say something about that complaint. I mean, we are listening, but in that case, I cannot actually do anything about it. This is the requirement. Another thing is that I'm almost done with the with the exam, with the midterm, grading it, and I'm very surprised that actually very few people attempted to solve the last question. So the programming question was like more than half was empty. That's quite bad this year. I haven't seen this bad. I don't know what you are trying to do. Maybe you're thinking that you can actually do this without it. And those questions were like very, very simple ones. I mean, I was expecting them to be just very, very easily done by you, like a few lines of code. And this means that you haven't learned programming. And I'm kind of worrying now that how would you actually do the homeworks if you haven't learned Lisp? So this is another thing that I need to check again. But if there are any problems regarding that, let me know. But don't tell me that don't do it this way, but suggest me some, let's say, how we can improve. Perhaps the only thing that we didn't do this year is we didn't do a PS session on Lisp. In the past, we have done it. I don't know how useful it was. I thought it was not that useful. Therefore, I didn't do it this way this year. And there was another reason that actually the TA for the course left this position here for something else. So we have only a part-time TA that is actually trying to do the requirement for the rest of the semester. All right, so let me know if you have any further comments or questions regarding this aspect. So last time we started to talk about C++, and we discussed virtual functions, and the question was, we have gone through these slides, but I'll talk about them anyway. The question was, if I have a virtual function like this in this thing, like you have the f and g function, and these functions can call each other, assuming that they are calling each other. The question was, how do they know which function to call in this case? So if I have an instance of class A, an object A, and if I actually try to call G in the virtual function f, how is it going to actually map? How is it going to know which one it is, right? So this is done simply using this pointer. And again, I mean, you need to figure this out. This is a problem, right? So you need to actually somehow tell your compiler needs to be able to actually tell which function it is that I'm trying to call. So the way that C++ actually does this is very simple, similar to the vtable. It says, okay, the code, that first code that you see here, right? So this code is actually converted to another type of a code after the compilation step. And the compilation step, you add another variable or argument, and that argument is created as a pointer or an object to itself, right? So that this pointer or this object here is actually a part of the function now, and you actually call this with this guy here. Therefore, now I know which G this is supposed to be because it is this part of the G. All right, so very simple. This pointer can be used in member function this way. Can be used to return a pointer to object itself and pass the pointer to object itself to another function and so forth. So very simple idea, right? So it's not a big deal. Regarding the non-virtual functions, how is the code actually for non-virtual functions found? It's very simple, similar to C, ordinary non-member functions. Compiler generates function code and assigns an address to it. And then that address is actually of the code is placed in the symbol table next to that particular function name. And then at call site, address is then taken from the symbol table and placed in the compile code. And that's as simple. Now, here you have another possibility or another, let's say, feature that C offers, this C++ offer, this overloading. Overloading is actually resolved at compile time here. So you have the same name, function name, with different types of arguments. So you can actually define it that way. And this resolution actually happens at compile time. So after the compile time, you know which version of the code that you'll be using. Therefore, you'll probably rename them in your symbol table accordingly. All right. So if you have two overloaded functions, f, you can call one of them f1 and one of them f2, and then find the right code at compile time to actually call when and change the, let's say, internal name of that function accordingly. So this is not runtime lookup of virtual functions. You have to be careful. Okay, so one question, why would you actually have these two things? One is overloading and one is this runtime lookup for virtual functions, these two capabilities, two features at the same time in a language. Why would you have that? Why would I need overloading? What is the use of overloading? For constructors, okay. Why? Why do I need overloading in constructors?
We have different number of parameters.
Okay, so you are saying that I may have different ways of actually constructing a class or constructing an object, okay? All right. What else? Yes.
To ensure polymorphism in general.
Say it again.
To ensure polymorphism in general.
Polymorphism. Okay. Now, what is polymorphism?
I don't know how to define it.
You don't know how to define it. All right. So he's saying that there is this notion of polymorphism, and it must be. I mean, you should do some sort of overloading for polymorphism. All right. We are going to come back to this one, and overloading and polymorphism are different things. Overloading doesn't actually directly serve. So polymorphic, the definition of polymorphism is you have an algorithm, and that algorithm actually can work on different types of data, different types of, let's say, input. The algorithm is the same. Like, let's say, if I am printing a list of things, right? So I can print that list of things for an integer, for a string, for something else, right? So the algorithm stays the same. I'm listing and I'm actually printing 1, 2, 3, 4, 5, 6 this way, right? And the algorithm is the same, but the way that actually I may do things differently for different arguments. Like if it's a list of numbers, I may need to do something different than if it is a list of, let's say, list of strings or something like that. Overloading is kind of different, right? Overloading is actually, you are defining different behaviors, different algorithms for perhaps the same input or maybe for different inputs, right? Someone mentioned actually about a constructor, right? So you say, okay, I may have to have different ways of constructing a class or constructing an object, okay? Why? Because you would actually probably have different ways of constructing it. Maybe in one way you have a specific, let's say, maybe a default constructor. In another way, you define a parameter, and with that parameter, you actually do a different type of construction algorithm, or with another set of variables or arguments, you might have different algorithms. So this overloading helps you to actually achieve some result that actually requires different algorithms. So the code changes. Whereas in polymorphism, your code stays the same, algorithm stays the same, but the arguments change. So they are quite different, not a little bit different, they are quite different. And polymorphism, of course, has a lot to do with typing system. And overloading doesn't need to be directly tied to the typing system. Right. We are going to talk about that a little bit later again. But in this case, overloading is actually resolved at compile time, and it's not the same as, let's say, runtime lookup of virtual function. It's quite different. All right. Now, as we said in the beginning, C++ was designed with one of the design ideas were around code reuse. So if you recall, last time we said you can actually look at an object-oriented programming language as a paradigm with several different things. Like one particular view is you look at it from how do you generate an object? How do you generate an object of, rather if you are using it, let's say, with classes or something like that, doesn't matter, but you have one view is actually how you define the behavior of creating that class and how that it actually does, whatever actually behavior it creates. That's the programmers of the class behavior versus I have objects and I want to actually just interact with these objects. This is the user of those classes, user of those objects. Now, we said C++ kind of merges these two things, and it pays a great attention to actually how that actually is done, how it is done in terms of especially code reuse. And that part is related to the concept of inheritance, right? Now, when you take that, the particular design choice actually allows us to define also multiple inheritance, right? So this is, again, a choice of C++, right? And the basic idea is you inherit, actually, you take some implementation, some behavior, some functionality from your, let's say, base classes, but from independent classes, not just one base class, one class that you're deriving behavior from, but multiple of them, and potentially they are independent from each other. And we are going to see in some cases that those classes will be, or those, let's say, classes will not be independent. They might be dependent as well. And that's another complicated behavior that we are going to see. But the basic idea here is that I may have, let's say, classes that I inherit behavior from, but not necessarily just from one class, but perhaps from multiple classes. This is, again, some of the terminology comes from biology. Like if you have, let's say, parents, you'll have, let's say, features from both parents, right? So you'll inherit some features from your, let's say, mother, and then some features from your father, and so forth. And you assume that those features are independent. Those two classes or whatever you are inheriting from is they are actually independent from each other. So you have a simple example here. We have things like shapes, very generic definition. And we have an instance of that shape as specified, again, as rectangle, right? And then we have some other concept like some sort of a counter, counting references of something, right? So you have two different things, shape or rectangle, and then some sort of a counting mechanism, reference counting mechanism. Now, what you can do is, in principle, you can actually combine these two things and inherit behavior from these things that actually can be coexisting together. And that will actually create a kind of a new behavior, like in this case, reference counted, let's say, rectangle. Now, the counting part of the thing is going to come from your reference counter, and the shape part of the thing is going to come from your from the rectangle and shape and so forth. So here we are interested in, again, code reuse. I want to actually define the behavior of reference counted rectangle. Shape part of that should come from rectangle or maybe from shape if it goes up that level. And perhaps the reference counting part should come from reference counted class. Now, this of course brings us quite a bit different problems. The first problem is going to be name clashes. The question is, if I have these two independent, what I call them independent, it's going to be obvious now that I am inheriting behavior, I am inheriting features from these 2 or 3 or 4, whatever, independent classes. The question is, if there is a name that actually used in both cases, in both classes, by both classes, like in this example, I am actually inheriting behavior from A and B, right? This is how you would actually do it. So if you were having only one class that you are deriving from, you would actually have only one of these, but here I have 2 classes. So I am having multiple inheritance here, all right? And it turns out that actually class A and class B have the same named feature, method, function, behavior, some sort of a behavior that is common to both of these classes. The question is, when I actually call this guy, when I call this inherited behavior, the question is who is going to actually be taking it over? Is it the behavior defined here, or is it the behavior defined here? I need to decide which one it is. All right. So this is called the name clash. And there are several solutions. Again, these solutions are obvious. This is not a rocket science. This is very simple. You can think about these things. You can, for example, say, okay, I would actually implicitly resolve this. How? The language resolves some conflicts with an arbitrary rule. I say, okay, perhaps let's say this way. I take the first one. If there is a name clash, and I have this order here, I'm making this up. This is an implicit rule. I'm saying there is an order, right? There is a first class, and there is a second class that I am deriving the behavior from. If there is a name conflict like this, what I would do is I would actually resolve it from the left to right. All right? I can do that. Nobody can actually harm me or blame me doing that. Or can you blame me? Can I do this one? Does this make sense at all? So I define an implicit rule. I say, okay, the first class that I see in the inherited behavior side will actually be using the behavior that I see, not the second one. Is this a good idea? Anybody? Come on. Why is it not a good idea? It is? But I resolve the conflict. I say, okay, conflict is resolved from left to right. If I have a name clash between these 2 classes, I will take the left one. The ambiguity?
For the one that uses it, because he needs to know if it's left to right or right.
Yeah, exactly. So this solves the problem. So I can actually, I'm solving the clash problem. Now clash is no longer there because I know the behavior. But how easy that behavior from the reader's perspective or from the writer's perspective, right? Now, the writer of this class, the class C, needs to know that the order is important. And in the case of name clashes, it will be the first one on the left that will actually be preferred over the second one, and so forth. This is very, very bad because now I need to know, I need to understand this behavior. If you recall, how am I going to actually write this down? Where am I going to write this down as a designer of that language? Where would you put this definition or this let's say rule? You are going to have a book, and then in this case, your book is going to have probably a section naming, okay, name clashes, and then in the name clashes case, it works this way or this way or this way. Now, what I'm doing is I'm making the learning of this language, the learning curve of this language is going to be quite steep. And probably there might be some unseen problems later on, especially if I have, let's say, things like these. If I have, let's say, this one also has some, let's say, maybe multiple inheritance. So this is quite difficult to solve it this way. This arbitrary rule could be okay, but it will be very difficult to communicate to the users of that language. And this is very important because the simplicity of these rules will make the learning of that language quite easy. And complexity will actually create problems from perhaps from the safety perspective as well. You can actually also assume some explicit resolution. You can say, okay, programmer must explicitly resolve the name conflicts. You can say, okay, hey, program, you do it. I don't care. I'm not going to take any actions, any, let's say, implicit actions. If there is a name clash, perhaps I can actually let you know. I can say, okay, there is a problem here. There's a name clash, and you'll solve that name clash problem. I don't know how you can solve it. All right. Another option is actually more strict approach to this one. You say, okay, I'm never going to allow any name clashes at all. So these 2 classes, 3 classes, 4 classes that you are going to be inheriting behavior from, they're not going to have the same name, same methods. They will have all different names for their methods. Okay, of course, this is a quite a kind of a restriction, quite a bit of a restriction. Now, from the programmer's perspective, programmer needs to actually have control over, let's say this, in this case, not just C, class C, but also class A and class B. If class A is written by this person and class B is written by that person, then we have to make sure that if I want to use them both, and if they decided to use the same F function, right, then I have a problem. I have to actually either ask them to change their names somehow, or I cannot just use them. So this is a restriction that is going to come with this one, right? The question, as we see here, none of these are the best solution. It has advantages and disadvantages. Each of them have their advantages and disadvantages. What C++ does is actually it assumes that some sort of explicit resolution is actually done. Again, this might be a problematic because you are actually asking the programmer to explicitly resolve this thing. Now, how much of it is going to be actually enforced by the compiler for the safety purposes? You have to be careful with that. Of course, you can repair this example by writing a function there, and then you actually, let's say, in this C, you write your function again, and then you call whatever function you want to actually call. So you overload, or not overload, you actually overwrite that function, and you just say, okay, I'm going to call A instead of B. So this is a kind of an explicit resolution, right? Ambiguity is gone. You can preserve the dependencies on A, right? If F changes, then CF changes as well. This is good. So it's a reasonable solution. This type of a thing is a reasonable solution. Now, what happens to the V table when we have multiple inheritance, right? So we have to think about that. Does it actually complicate things with V table? Again, V table was a very nice solution because it actually get us just one indirection to get the right function lookup at runtime. So this is as, let's say, efficient as it can get. Now, does this complicate? Does this get any complicated when we allow multiple inheritance? So we have 2 things here. You see, class A has a virtual function F, and class B has virtual functions F and G. So there is the same naming in B, and class C is actually driving behavior from both of these classes. So there is a multiple inheritance there, and we are actually explicitly defining the behavior with regards to f function. So we are going to actually put something in the f function and say, okay, it's going to be either choosing this one or that one. And we have, let's say, three instances here. PC is the C class, an object of C class. PB is actually a copy of it, and PA is a copy of it again. So there are 3 pointers to the same object, but they have different static types, right? So when you look at actually the object and class, or at this V table part of this thing, PA and PC will have this beginning of the V table with the A data, right? And PB will have the virtual pointer for the B data, and B object as well as the C object there, C data there, right? So in this case, offset delta in V table is used in call to PBF because again, CF may refer to A data that is above the pointer for PB, sorry. And call for the PCG can proceed through C as B through the V table. All right. Good. So this is reasonable. Now let's look at actually another complication that comes with this. When you allow this type of a behavior, this multiple inheritance behavior, now you could actually end up with, there is no reason you cannot do this one, multiple inheritance of this form. This is a simple form where you have actually a class that is derived from or inheriting behavior from 2 different classes, but these 2 different classes are not independent, meaning they are both derived from the same class. So there is a parent class to those 2, and you are actually inheriting the behavior from these 2 classes having a common parent. Now the question here is, this is a question now you have to sit back and look at these 2 things that we were discussing, right? One is the implementation of the class, and the other one is actually the usage of it. So in the usage part, we were talking about interface, meaning the allowable interface or allowed interface or allowed, let's say, messages that are accepted by these classes or these objects. And the question also regarding the inheritance, the code. Where does the code come from? When we look at actually, let's say, the interface and the implementation, are they inherited twice? Right? So this is the question that we have to ask. And also, what if definitions actually conflict? And this is called diamond inheritance in C++. Again, you would not see this one in Smalltalk. Why? Why wouldn't you see this in Smalltalk? There is no multiple inheritance. Therefore, if you don't have a multiple inheritance, you will not have actually this type of behavior at all, right? Now, you have the standard base classes. D members appears twice in C. So the question is, you see that here, the C will have B's member, the base class, and they appear at least inheritance-wise, they will appear twice in C, right? Now, what we can do is you can avoid duplication of base class members. So you can actually add something like here, make the D a virtual class. So therefore, at least the inheritance code will be will not be allowed. So there is no code for the behavior in D. Therefore, A and B must implement their behavior. Therefore, I'm safe, at least from the inheritance perspective. All right. So avoiding duplication of base class members, and this requires additional pointers so that D part of A and B parts of object can be shared. All right. So I'm not going to go too much detail. Into this one. You have studied this quite a bit in your object-oriented programming course, but this behavior, this multiple inheritance in C++ actually is complicated, right? Again, the complication comes from the kind of the need for an efficient lookup mechanism. So if you actually relax the lookup mechanism a little bit, perhaps you could solve this one. But this type of a thing, if I had a dynamic lookup here, I could probably do a little bit more, it could be a little bit easier. But this is a problem, and we are going to see that this problem can be solved in let's say, in other ways. And we'll see Java actually doing this. This will be our next topic. Any questions? Do you use multiple inheritance in real life? Can you give me some examples? C++ people using multiple inheritance. Can you give me real life examples, not shape and stuff that I have here? Someone said no, they don't use it. I respect that.
Sir,
fine.
adapter
Yes.
patterns, pattern of adapter uses multiple inheritance in C++.
Pattern of adapter. What is an adapter pattern?
We have to change one class to another, but we need to have a middle class, so it adapts one class to another, and it uses multiple inheritance in C++.
So who is this? Let me see. Who was who's
Salih.
Okay, Salih was saying that, okay, we'll have this behavior obviously used in an adapter class where you actually convert a class to one class to another class, and then you need a middle class to actually do this behavior. All right. Anybody else? Has anyone used it in any real life examples? No? Yes? Sure.
Is there any example of multiple inheritance in nature?
In nature, multiple inheritance in nature.
Yes.
Right. In biology, you mean? Could be. Right. It could be if someone is. Of course, inheritance in biology is a different thing than inheritance that we are actually doing here, right? So it's an analogy, but it's not exactly the same thing. And you can have, let's say, this is a taboo perhaps, but if someone's, let's say, parents are actually sharing a common ancestor, that could actually be maybe a grandparent or maybe a grandparent is common. That can happen. Okay, but the question of actually the usefulness of this multiple inheritance, it's clear, right? So what you have is you can actually the basic idea is you can actually inherit behavior and combine them into a new, let's say, new behavior, new object. So makes sense, but in C++ we have the problem of these type of diamond type of, let's say, multiple inheritance problems, and you have to solve them. And we are going to actually see how it is solved in Java. So let's start with I don't know. I don't want to start right now. So let's take a 10-minute break and we'll continue at 3:20.